Hello and welcome to the 41st lecture in this series. And I had to stop in the middle of a computation last time. So I was trying to calculate the Lie bracket on the Lie algebra of GLNR. And we wanted to see that if we identify the Lie algebra with the tangent space at identity, which is MNR, then the Lie bracket of the two left invariant vector fields corresponding to A and B is just the matrix Lie bracket AB minus BA. And for that I started with this lemma which describes all left invariant vector fields on G. Namely, if you start with A in the tangent space at identity, then the left invariant vector field corresponding to A, which I denote by XA, is just given by its value at P is PA. And we did the computation of this. So now let's proceed with the main computations. Now let's come to Lie bracket. Let AB belong to MNR, and let's keep in mind that this is tangent space at identity of GLNR. So I will continue with the same notation, X subscript A, X subscript B. Now what I want to do is, let's do XA, XB. So I want to understand this left invariant vector field. So I want to see what its value at a point P is. And I'll act it on a C infinity function phi. So phi is a C infinity function on GLNR, on the manifold. Right. So okay. Now this is, I'll just go by definition. So this is XA at P acting on XB phi minus XB at a point P, XA acting on phi. So one wants to understand this XB of phi. Yeah, before that, now what I would like to say is that instead of considering all functions phi, what I'll do is, it's enough, I claim that it's enough to understand its action on. So we'll restrict ourselves to take phi to be the functions phi of x equal to just xij. So actually I should say phi ij rather, because it's dependent on ij. So here I'll say for ij lying between 1 and n, take phi of x equal to xij, i.e. phi is the projection map, phi equal to pi ij. So this is the projection map from Rn squared to R. So this is MNR. So it will project to the ijth coordinate. I mean, this is, well, with the appropriate numbering. Right. So it's enough to take. So let's see what happens with these, the action of XA, XB on these things, Xij. So for that, now let me look at this term here. Rather, not even that, I'll just look at the thing inside the brackets. So I'm just going to look at this. XB phi, remember that this thing is supposed to be a function on the manifold GLNR. So I want to understand its value at a point Q. And we know that this by definition is, remember that xf at x is x. This was the way the function arose. So this is the same thing as xb at the point Q acting on phi. Now we know exactly what xb at Q is. This is by the lemma that we just proved. This is PA. This is Q, in this case it would be QB acting on phi. Well, when we say QB acting on phi, one has to keep certain conventions in mind. For instance, here when I said XA at P is PA, now A is just an MNR element and P is a GLNR element. So the product is again just an element of MNR. So this is just an MNR. However, this is supposed to be thought of as an element of the tangent space at T at P of GLNR, which is still MNR. This is still MNR, but except that partial derivative. So essentially, so for to make sense of this, what I wrote here, I'll just write an aside. So if V is a vector space, we know that the tangent space at any point P of V, actually, and here to be more even more explicit, I'll take an open set just like this here. GLNR is open inside MNR. Let me do that here as well. U contained in V open, P in U. We know that the tangent space at any point is equal to V. Now this equality means that means the following. So if I start with V in V, the corresponding element of TPU is, so in fact let me just take Rn, Euclidean space, for clarity. So instead of dealing with any arbitrary, after all we are in the realm of Euclidean space, standard Euclidean space here. So Rn here, and then Rn, and here too it would be Rn. Oops. Rn and Rn. So yeah, but if you start with any V in Rn, if the tangent vector at the point P is would be, so I write V in coordinates, V1, V2, Vn, then this goes to the Vi, the derivation given by del xi. The main thing here where P occurs is in the derivation part. So I evaluate the del xi at the point P. So even this V in Rn of course has nothing to do with P, but if this isomorphism will keep track of the point P in this way. So it's Vi del xi at P. So here too, when I say TP GLNR is MNR, it's the same thing here. So if I start with an element of MNR, I get a derivation at the point P via this prescription. So Vi del xi at P. So let's do that. Here of course the one is dealing with Rn squared rather than Rn. So for instance here when I write QB at phi, one has to remember that this QB is supposed to be a derivation at the point Q. After all, so this I'm supposed to get a tangent vector at Q. So let's do, so this is for any phi. Now I'll plug phi of x equal to xij, namely the projection map pi ij. So in that, but first let me write the general expression. So this is QB, the coordinates of this element of Rn squared, QBij. It's exactly like what I wrote here, the same thing that whatever I wrote here, I'm just using the same thing here, and it would be del by del xij of phi. Now the main point here is that this is evaluated at the point Q. Right. So just since I'm going to use ij for this function phi, I don't want to use the same ij as summing index. So let me rewrite it in terms of some other indices. Kr del phi by del x Kr of Q. Now let's do this business of taking specific functions phi and see what we get. Let's take phi equal to xij. If phi of x equal to xij, then all the partial derivatives of phi will be 0 unless this index pair Kr is exactly equal to ij. Then and only then will I get this to be, then I'll get it to be 1, otherwise it will be 0. Then xb phi at the point Q will be exactly QB at the point at the ijth entry of QB, the matrix QB, because all the other terms here will vanish. Right. So which using the definition of the matrix product, I can write as Qik and then Bkj, k equal to 1 to n. Okay, so in short, another way of writing this is i.e. xb of phi, the function xb of phi. Remember, q is supposed to be the variable here, and we are trying to understand this function xb of phi. So this, if I don't want to mention the variable, its xb of phi is, now this function qik is just the projection, the ikth projection acting on q. So this is pi I k bkj. So I get something like this. So pi ik is the ikth projection map from MNR to R. So all it does is, if I input a matrix A, it gives me the ikth entry. So this, yeah, okay, so fine, that's what we have. And then finally, yeah, now let's return back to, so this was just one term we had picked out. We are trying to understand this term here. Of course, if we understand this, we understand the second one as well. The computations for this will be exactly the same as this. So now that we have a formula for this, I can do one more derivation action. And let's see what we get. So with this in hand, So xa at p acting on xb phi. Of course, all this was done for the specific, the simplification was done with the specific function phi equal to x. So phi, the function phi is pi ij. For this thing, the computation turned out to be this. And let's continue with the same function phi. And so this will be again, so whatever I have here, so it's xa at p. So essentially I just plug this, whatever this expression here inside this and take xa inside the summation sign. So it will be xa at p acting on pi ik. Bkj is a constant anyway, times bkj. Right, and here again I'll use the fact that xa at p is nothing but pa of pi ik bkj, and by the same logic that we went through here, here that this xb at, so whatever we did for this q and b, now we again do it for p and a, because we are again now acting on a projection map just like we did here. So ultimately the same logic will leave us with, here we were left with, when we acted it on this, we were left with this expression pi ik as a function, but the only difference is that between this computation and here is that we are just interested in the value at the point p rather than we don't have a function. So we just take a specific point and we'll get this expression here. So what I'll get is pa at ik because here right, so this is the part I'm using, actually this is the part I'm using, the similar thing here, and so I'll get pa at ik. And then I have bkj, and I'll get, so this thing bkj is the same, right. So and this of course is the ijth entry of the matrix PAB, the ijth entry of this matrix PAB. Now if I do the same thing, same considerations will apply for the second term here, except that a and b are switched. So it's clear that the second term will give me similarly xb p xa phi as p ba ij. In fact, yeah, I don't have to do the computation. I just this a and b were arbitrary, so the same thing will apply here as well. So finally what one gets is, therefore the Lie bracket of xa xb at p acting on the special function pi ij turned out to be, so the ijth entry of PAB minus BA this. So this is what we get. What we wanted to say is that we want this to be actually equal to So this is, I'll put a question mark here. Is it the same thing as we wanted to claim that this is the same as the left invariant vector field corresponding to the matrix product xp minus xa at p acting on pi ij, because that's the statement, the original statement was that. In fact, the original statement which I wanted to say when I said under this identification, if we identify G with this, then this happens. In the language of this XA business, it's i.e. X AB minus BA equal to XA XB. So this is what we are trying to prove. So you're right. Okay. So we have this equal to pi ij. Now this, so I want to know whether this is equal to this, and I have reduced it to this expression. And we know that this is equal to P AB minus BA. After all, we have an explicit description of the left invariant vector field like this, and this is supposed to act on pi ij. And we have already seen this. When a matrix left invariant vector field, when a matrix acts on when a left invariant vector field acts on this special function pi ij, what one gets is essentially the qbij, and here it is pab minus ba ij. It's the same calculation that was involved in this green box here. So we have used that twice. So and this are the same. So, but however, what we have done is we have checked it just for these xa, xb, p acting on this function pi ij for any I and j. We are getting the same values. What about for arbitrary functions? So xa, xb so I say that I claim that this implies that this equal to xab minus ba at p for any phi in this C infinity GLNR. Now this is nothing to do with GLNR or anything, so it's a more general fact. So let me just state it like this. So more generally, let's just take an open set in Rn is open, and you take a point inside that, and I take two vector fields on this open set. If I want to claim that this equal to this, then if and only if I just have to check that they are equal on the coordinate functions. So if and only if xp, the projection maps equal to yp pi I for all I. And the reason is quite simple. It's just that we can express xp as summation ai del by del xi at p and yp as bj del by del xj at p perhaps yeah, okay, now let's I've already used the index I and j for these things. So for the projection map I'll use pi k. So suppose xp pi k equal to yp pi k for all k. Well, if we act xp pi k is summation ai del by del xi acting on pi k at the point P. Now this is the projection map, in other words the coordinate map into the kth coordinate. So the only term which will survive is the kth one. So this will just give me ak. So similarly this yp pi k is bk. So what happens is that you just end up with, therefore ak equal to bk, k equal to 1 to n. Therefore the two vector fields, the two vectors, these two vectors are the same, and that is what we have used. So it's enough to check it on these projection maps, right? So that proves that we have an explicit description of the Lie bracket of left invariant vector fields as a Lie bracket of matrices. And in fact this carries over, this description of Lie bracket, this carries over to the subgroups of the GLNR that we have been looking at, namely ONR and SLNR. So I'll just say a couple of words about that. So lemma. So let me write it like this. This description of the Lie bracket carries over to SLN, ONR and SLNR, which are the other two Lie groups we have been looking at. They are there's. So the lemma is, let G be a Lie group, H contained in G, a submanifold which is closed under multiplication and inversion. Then then H is itself, H is a Lie group H is a Lie group, and if V belongs to the tangent space at identity which is contained in tangent space at G, XV, YV are left invariant vector fields on H and G. We have XV equal to YV restricted to the subgroup H, i.e. XV is the inclusion map I related to YV. So I'm saying something quite obvious here actually. I'm just saying that if you have a submanifold which is also a subgroup, then the first part is that H is itself a Lie group. So this amounts to just saying that multiplication and inversion are smooth. We already know H is a submanifold. and the fact that it's closed under multiplication and inversion means that H is a subgroup, but it's a Lie group. So the multiplication inversion operations are smooth simply because H is a submanifold. So that part is clear. Once it's a, right. And now if V is in the tangent space at identity, I can extend V to be a left invariant vector field on this Lie group H and also on the Lie group G, because the same V belongs to two different tangent spaces, this and this. I'm saying that the left invariant vector fields, the left invariant vector field on this H is just a restriction of the left invariant vector field Y on the big group. And with that, I'll be able to describe all the Lie brackets on these groups ONR and SLNR. So I'll complete this next time. So we'll end this lecture on this with this specific lemma. Okay, thanks.